Hello everyone, welcome to the series of lectures on the course Calculus and Numerical Methods. This is part 6 of the first chapter, the real number system, and the title is LUB property of R and its applications. Outline of this video: LUB property of R, which is also known as order completeness of R, and Archimedian property. Now, this LUB property also, LUB is a short form for the least upper bound. Okay, you all already know what's the least upper bound. You can also call this as the supremum property of R. Okay, so this is one of the most important properties in analysis. Okay, so it has lots of applications, as we'll be looking at the applications in the coming lectures and even in this lecture. So this LUB property of R, it is also known as order completeness of R. Okay, both mean the same. So since the textbook is referring to LUB property of R, I will stick to LUB property of R. Okay, so you can also call it order completeness of R. Now what this says is every non-empty subset of R which is bounded above in R has a least upper bound in R. Okay, every non-empty subset of R which is bounded above in R has a least upper bound in R. That means you take any non-empty subset you like in R. Okay, it should be a subset of R, and that set what you are taking should be bounded above in R. That means there should be a upper real number which is an upper bound of your given set. Then you will be able to find the least upper bound for that set. Okay, so I can also state this as given any non-empty subset A of R, so a subset of R which is non-empty. So given any non-empty subset A of R which is bounded above, what it says, it will have a least upper bound. That means there will be a real number which is a least upper bound of this set. Okay, so there exists a real number, an alpha in R, such that alpha is the least upper bound of A. Okay, so this is an axiom which is assumed to be true. It doesn't have any proof. Okay, as you know, axioms don't have proofs. So we will agree to the fact that if I take any non-empty subset of R which is bounded above in R, it has a supremum or a least upper bound. Okay, now when I say this bounded above in R, it's very important to mention this R here. Okay, because this property, least upper bound property, it does not work for the set of rational numbers. Okay, later on I'll be giving an example of a set which is a subset of rationals, and this property does not work for that set. So to say that it is bounded above in R is very important. Okay, even you should say that LUB property of R. Okay, because there are some sets for which this property does not work. All right, now we will look at one application of this property. Okay, that is again a very important property. Again and again we will be using this property in upcoming lectures. So this is called Archimedian property. Okay, this is called Archimedean property. So let me state this. So this property says that the set of natural numbers is not bounded above in R. Okay, so let me state it. N is not bounded above in R. Okay, that means if you take any real number, you will be able to find natural numbers which are bigger than that natural number, that real number. Okay, so I can also state this as, that is, given any alpha in R there exists a natural number n such that n is bigger than alpha. This is what I want to establish. Okay, so let's prove this. What I'll do is we'll assume that n is bounded above in R and we will arrive at a contradiction. Okay, so this is proof by contradiction. So let's assume that n is bounded above in R. Okay, so I'll assume that n is bounded above in R. Okay, so I have a subset n, that is the set of natural numbers of R, which is bounded above. And the set of natural numbers is non-empty because I can pick up natural number 1 which is there in this set. So I know that this is a non-empty subset of R. Now let me look at the least upper bound property. What does this say? It says if I take any non-empty subset of R which is bounded above in R, then it will have a least upper bound in R, right? So I will apply the least upper bound property here because I am assuming that natural numbers is bounded above in R. So this natural numbers is going to have a supremum. Okay, so therefore by least upper bound property, there exists a real number alpha such that alpha is the least upper bound of the set of natural numbers, right? So alpha is the least upper bound of natural numbers, or you can say supremum of natural numbers. Now what do you mean by alpha is the least upper bound? It is an upper bound first and it is the smallest of all the upper bounds, right? So because alpha is an upper bound, all the natural numbers will be less than or equal to alpha because it's an upper bound of n. Okay, so therefore alpha will be bigger than or equal to all natural numbers. So k will be less than or equal to alpha for every k in n. Okay, every natural number k is going to be less than or equal to alpha, right? Now let me put this on a number line. Okay, just to get a better idea of it, let me put it on the number line. I have alpha here and I'm assuming that all the natural numbers are on the left of alpha. Okay, they are here. Okay, they are somewhere here. That's my assumption. Now if I look at the number alpha minus 1, okay, if I look at the number alpha minus 1, that will be somewhere here less than alpha, 1 unit less than alpha. Okay, so now I know that alpha minus 1 will be strictly less than alpha because I am subtracting 1 from alpha. So the result will be definitely 1 unit less than alpha. So it has to be on the left hand side of alpha. Now I am assuming that alpha is the smallest upper bound of n. It is the least upper bound of n, right? And alpha minus 1 is a number which is less than alpha. That means alpha minus 1 cannot be an upper bound of n, right? By the characterization of supremum, if you see, alpha minus 1 is not an upper bound of n. And when do you say that a number is not a upper bound of a set? When there is an element of the set which is bigger than this number alpha minus 1, right? So alpha minus 1 is not an upper bound. This implies alpha minus 1 is not an upper bound of n. Okay, that means I'll be able to find one natural number here which is greater than alpha minus 1. Okay, so there exists a natural number, let's say n I have already used. No, let me pick up some other notation, let's say capital N. Okay, so there exists a natural number capital N such that n is greater than alpha minus 1 because alpha minus 1 is not an upper bound. right? So what this will mean, I can add 1 on both sides. Okay, so that will give me alpha is strictly less than n plus 1. By adding 1 on both sides, I have this. Now capital N is a natural number, and if I add 1 to a natural number, again I'll be getting a natural number. That means this n minus 1 is a natural number, and we have found one natural number. You can give some name to this. Let's say, okay, alpha is less than some notation, q's n naught, say, okay, where n naught is n plus 1, okay, which is again a natural number. Okay, so we have found a natural number n naught which is greater than alpha, right? So that's a contradiction because alpha was the least upper bound of n. So all the natural numbers should have been less than or equal to alpha. But I found one natural number n naught which is greater than alpha. So that's a contradiction. And why we are getting the contradiction? Because we assumed that n is bounded above nr. Okay. So this is a contradiction too. I can name this. I can give some name here. Let's say star. Let me put a star here. Yeah, I'll put this star. So this is a contradiction to star. Why we are getting this contradiction? Because we assume that the set of natural numbers is bounded above in R, and hence we conclude that natural numbers is not bounded above in R. Okay, so this is the first form of Archimedean property which says the set of natural numbers is not bounded above in R. I hope that's clear. Next, we will prove this. We will first state the second Archimedean property, and we will show that the first and the second are equivalent. Okay, so I will put that as a theorem. Okay, so the following are equivalent. The following are equivalent. So the first one is the same property that I have stated just now, and we have proved it. I will call it Ap1, Archimedean property 1. Okay, so that says n is not bounded above in R. Not bounded above in R. And the second one says, this is the second form of the Archimedean property, and both are equivalent. Okay, this says given any real numbers x and y, given any x comma y in R with x positive. Okay, so I'm looking at any real numbers x and y with the condition on x that x is positive. Okay, so if I have this, then there exists a natural number small n, then there exists a natural number n such that n into x will be bigger than y. Okay, so these two are same. Okay, this is just a you can say reformation of the first one. So because x is positive, the number 1 by x will be well defined. So if I multiply the number 1 by x on both the sides, what I'll have, n will be greater than y by x, and that y by x will be a real number. Okay, So again it says that if you take any real number y by x, I can find a real natural number n which is bigger than y by x. Okay, so it's just another form, you can say, of the first version of the Archimedean property. Okay, I want to show that these two statements are equivalent. I have statement ap1 with me, I have statement ap2 with me. Okay, and we have already seen how to show that two statements are equivalent, right? So first we will show that ap1 implies ap2 and then ap2 implies ap1 back. Okay, so this will have two parts. So the first part is we will show that ap1 implies ap2. Okay, so let's assume that n is not bounded above in R. So suppose n is not bounded above in R. And what we need to prove? We need to prove that given any real numbers x and y with x positive, there exists a natural number n such that nx is greater than y. Okay, we will assume that this is false. Okay, so this is a proof by contradiction again. Okay, so that's a proof by contradiction. So what we will what is the negation of this? That is what we need to assume. So we will assume that there exist real numbers x and y with x positive such that for every natural number n, this condition is not true. So again, universal will change into existential and existential will change into universal. Okay, so let if possible, okay, there exists real numbers x and y with x positive, okay, such that this condition is not true. That means such that nx is less than or equal to y. Okay, negation of this is this. Correct. Now what I know about x is a strictly positive real number, so I can talk about its reciprocal. That will be well defined 1 by x. Okay, so what I can do now, I can multiply 1 by x on both the sides, so that will give me n is less than or equal to y upon x. Okay, where now y is a real number and x is a positive real number, so y by x again will be a real number, and this statement is true for every natural number n, because that's what we are saying here, such that nx is less than y. I forgot to mention, such that nx is less than or equal to y for every natural number n. Okay, because here we are saying there exists a natural number, so its negation would be for every natural number. So for every natural number n, nx will be less than or equal to y. Correct. That means n will be less than or equal to y by x for all natural numbers n. Again, that means the real number y by x is acting like an upper bound for the set of natural numbers, but we are assuming that the set of natural numbers is not bounded above, so that's a contradiction, right? So this means y by x, this real number, is an upper bound of the set of natural numbers. Okay, so this is a contradiction to our assumption. That is, I can give some name again to this. Let's say double star I can use, maybe, because we've already used a single star. So that's a contradiction to double star. Okay, and why we are getting this contradiction? because we assumed the statement Ap2, the second form of Archimedean property, is false. Okay, and therefore the statement Ap2 holds true. Okay, so what we have done is we have assumed the first Archimedean property, the first form Ap1, and we have shown that the second form Ap2 is also true, right? Now the converse, we will have to prove that Ap2 implies Ap1. So I will assume Ap2 now, and we will prove that Ap1 holds true. Okay, so the second part will be to prove that Ap2 implies Ap1. So let's assume Ap2. So suppose given any real numbers x and y with x positive, if you have this, then there exists a natural number n such that nx is bigger than y. So this is my assumption. I have to show that the set of natural numbers is not bounded above. That means no matter what real number you take, that will never be an upper bound for n. Okay, so supposing I start with some real number. Okay, so let alpha be a real number, be arbitrary. So alpha is any real number. What we have to show is this alpha is not an upper bound of n. That means we have to find a natural number which is bigger than alpha, and we are done, right? Now from my assumption step, if I take any two real numbers x and y with x positive, then I have this. I can find a natural number n such that nx is greater than y. And what I want to do now, I want to find one natural number which is greater than alpha. Okay, so existence of n will come from here, from our assumption step. So if I choose x as my 1 and I let alpha y to be equal to alpha, the same real number which I picked up, then I'm done. Then what I'll have, n is greater than alpha, and that's what we need. Okay, so what I'll do, I will choose x to be equal to 1 and y to be equal to alpha. This alpha is this real alpha which we have assumed here. Okay, now as per our requirement, x and y are two real numbers with x is positive, 1 is positive. Okay, therefore by our assumption from here, there exists a natural number such that nx is greater than y. There exists a natural number n such that nx is greater than y, right? What does this mean? There exists a natural number such that x is 1 and y is alpha. That means I found a natural number n such that n is greater than alpha. That means this alpha cannot be a upper bound of the set of natural numbers. Alpha is not an upper bound of n. Okay, because I found a natural number which is greater than alpha, and alpha was an arbitrary one. So no matter what real number alpha you take, I will always be able to find at least one natural number which is greater than alpha. Okay, that means alpha cannot be an upper bound of n, and that means n is not bounded above. Okay, so the two forms of the Archimedean property are equivalent. Okay, if I say one, the other one will automatically hold true. All right, so these were the two forms of Archimedean property.